All right, afternoon, everybody. I know there was some excitement next door, right? So I hope everybody who wants to be here is here. But if not, oh well, I guess we can keep the door open, and as we get more that comes in, they'll come on in. So thank you for being here. I guess you're interested in this topic, which, I kind of classify people who are in the audience on a topic like this into three categories, right? Either you are a defender trying to help protect the grid, you are a homeowner wondering if your lights are ever going to go off, right? Or three, you work for a nation state, right? So is anybody in that third category there? No? Okay, good. Well, let's continue. Yeah, it's on. Test. Test. Mic check, 1, 1. Test, 1. We are on. I guess I could use the test. Test, 1. Mic. Awesome, thank you. I guess I'll hold both. I don't know if does the gain multiply, right? So yeah, this topic, taking out the power grid's middleman, right? So I'm Nathan Wallace, the co-author, person who actually did most of this work. I'm going to give credit to him. He couldn't make it today. He's actually attending his fiance's graduation. So I guess, before they get married, that's kind of an important thing. So just real quick, disclaimer, statements and opinions are my own, which may or may not reflect that of my current employer. Statements are based on generalized observations of the industry and may or may not represent any one particular entity or asset owner, right? So just general observations. We're not calling out any specific vendor or utilities in this presentation. This topic really, we're kind of diving in, taking a look at one of the devices, one of the types of technologies or devices that's used to control the grid. So it is a personal challenge of mine. Hopefully I can hold to it. Try not to reveal any specific vendor information, right? So if you're asking, okay, well, what vendor is this applicable for? Right now, we're not comfortable with making that public. So as far as personal background, pretty much engineer by training, work in the industry, in the electric utility industry. Did some intern stuff, drafting, relay settings. After I finished school, basically worked for a small utility here in Louisiana, doing maintenance, transmission, distribution maintenance, field type work, right? About that time, I saw someone who was able to hack into a smart meter. He reverse engineered the wireless spread spectrum protocol coming out of his smart meter. So I'm like, oh crap, I need to go back to school, right? So that's what I did. Went back to school, worked for a university lab doing digital forensics and control system cybersecurity. So it was a pretty cool marriage. Local law enforcement would bring us a cell phone, laptop, say, hey, can you recover some evidence for us? As well as we were hacking into PLCs, relays, and trying to figure out how do we protect these control systems? How do we protect the grid? So that's cool. I think I just got louder, so I guess I need to hold it closer, huh? So some volunteering efforts I'm involved with, Computer Society, IEEE, through and through, also Cyber Patriot. So that's a great mentoring opportunity. If y'all are interested, you can help some of the grade level kids get into this industry, as well as some standards, right? So there's a lot of technologies now that are coming into the grid. I think after this talk, there's one on IoT, right? So we actually have a task force within IEEE focused on how do you integrate IoT technologies into the grid? Because now there's use cases where if it's during peak demand, the utility can send a command and turn off your dryer, right? Turn off your coffee pot, right? If it's during peak demand, there's proof of concept use cases to pull power out of your electric vehicle to supply the grid. Okay, so cool technologies. So that's another effort that I'm involved with. As far as an outline of today's talk, background, right? We have to really create the context. What is this device that we're going after? Then we're going to get into some of the recon, exploitation. So this is really getting into those juicy bits, as well as a DOS attack, and then the next steps, right? This type of stuff, it's an evolving process. And hopefully by the end of this talk, I pretty much say this statement at every presentation I give. Cybersecurity in the power grid, it's about safety, right? In any control system environment, cybersecurity is a safety issue, right? Compliance is the last thing you should be worrying about, right? As you can see, some think it's only about compliance. So as far as today's grid, right? Today's grid is really comprised of two infrastructures. The first is the physical infrastructure. When you look up and see the distribution poles and the lines, that's the physical grid, right? That's that flow of electrons. And today's grid basically has this other layer, cyber, right? So right here, this is depicting basically all those communication paths. Some are wireless, some are wired, right? So this is those communication paths, as well as computation. We're adding more computational capability to the grid, not only inside the control center, right? So that's these blue blips, but we're also adding them on the lines, on the transmission lines, on the distribution lines. So what that means is, whenever you go driving down the road and you see this line, right? It just is a line, and then you'll see a ball just kind of sitting there. That's a sensor. Odds are that's a wireless sensor sitting there, sending this data, power flow data, via some wireless infrastructure back to some control center, right? So wireless and wired data, and then this massive influx of computation. And the reason I stress this is because some people, when they hear cybersecurity, oh, just protect the communication links. That's all you have to do. Nah, it's a little bit more than that, right? You have to make sure that the computational assets, the actual devices that are controlling, are secure themselves. So as far as security, this is the way I define it in our industry, the power grid. So the facet of reliability that relates to the degree of certainty that a cyber device or system will not operate incorrectly. And cybersecurity, right? The issues, they could be physical. If you break into a substation, take a bat to one of the panels, hey, it's inoperable, right? This actually happened in a utility over in California a few years back. EMI, right? So this is electromagnetic interference. Don't want to go into too much detail there. And then what we traditionally think of as cyber is basically digital, right? So going back to the previous slide, anything that has communications or computational capability. Now, if you look at all these different attack vectors, right, they're kind of represented here in this graphic. On the left is almost that accidental type stuff. Over on the right is really this malicious, right? Misconfiguration. So that's that open door there. There was a utility in Tennessee, right? So in our industry, in the electric utility industry, we have to meet some compliance standards with regards to cybersecurity, okay? Some argue that they're not as strict as they should be. Some argue that they're just policy standards and not actual technical engineering standards, right? But that's another debate for another day. But basically, whenever this specific utility in Tennessee went under, we're going to do ups and downs here. So, okay, when this utility in Tennessee did their first audit, over half of their firewalls were misconfigured, right? Over half of their firewalls were misconfigured. And this is when they did their first audit. I think it was maybe 07, 08 timeframe. Vendors themselves. A lot of times the utilities, they don't build the infrastructures. They hire contractors, consultants, vendors, system integrators to come in, right? So that's a potential vector. The Homer Simpsons of the world, right? That accident-prone insider. And then over here on the right, we actually have the intentional insider, which there's been plenty of examples of that. The lone hacker in his mom's basement, or actual nation states, right? So what are we seeing as far as the grid of things? This is a new coin, right? Kind of borrowing from this Internet of Things. We have electric vehicles. We have advanced metering infrastructure. I think one of the, pretty much, what is it? I forget the exact rollout, but one of the local utilities is about to start rolling out their AMI infrastructure where you're going to have smart meters on all your homes. And what this allows you to do, you forget to pay your bill, right? You get a letter in the mail. Forget to, if you don't do it by that next deadline, you get a little nastier letter, right? Third time, someone potentially 3 states away is hitting enter on a keyboard and your power is disconnected, okay? Distributed generation. So this is PV, photovoltaic, solar panels, renewables. Basically, we call them DR, distributed energy resources at the home. as well as right here on the right, distribution automation. So that's an example of a technology right there on the top right that you would mount on a pole, and you can control it from an app on your phone, right? This particular device is a recloser. Now we also, to manage all this distributed energy resources, we have what's called virtual power plants. I cringe, right, every time I hear that. Virtual power plants. I'm like, is that something VMware is going to run? You know? Right, so quote here on the bottom, I think I've overused this quite a bit throughout the years, but our expectations is that the modernized electricity grid will be 100 to 1,000 times larger than the internet. Right, when you count all the nodes that are going to be connected to the actual grid, all the sensors, all the devices, all the control capability, this VP, 100 to 1,000 times larger than the internet. So this goes back, this is an example as far as DER. This technology here, it's sold as consumer electronics technology, right? You bring these technologies now into your home, right? What Tesla sells those, I forget what they call it, like power packs or something. You know, it's the battery that just mounts in your home, right? And you can hook it up to your car. There's software inside. I think they actually Tesla just released a software upgrade to unlock some features and functionality in that pack just a few weeks ago. In a lot of cases, not just picking on Tesla, right? But in a lot of cases, this technology is managed what? Via the cloud, right? It's managed via the cloud. There's code, software on these devices to detect faults. So what a fault is in the electrical world, electrical engineering world, you know, it's basically a short circuit. You have a massive amount of current flowing where it shouldn't be, right? So things kind of heat up. You could start fires. So the idea is you want to be able to detect that fault and de-energize that line as quick as possible, right? Lightning strike, it's an example, can cause a short, right? Things fry, things short circuit. And you want to clear, we call it, you want to clear that fault as quick as possible. There's now software inside the home that's detecting these faults to clear these potential life-threatening issues, right? So that's a whole other talk again for another day. Example of system topology. So right here, let's see if I can get my mouse working, maybe. So right here we have generation, and when you talk about the electric grid, traditionally it's divided up into three categories, right? Generation, transmission, and distribution. So here we have generation. So this could be your coal, nuclear, natural gas. We have transmission, so we have substations that step up the voltage, push it out, and then this is utility scale renewables that are feeding the grid. And then we bring it back down, and we're here at the distribution level where, guess what, it serves as your home, right? You step the voltage back down, and it serves your home. And then here at this distribution level, we're adding more technology. And it's good, right? I'm not advocating against it. Just real quick, one example is a utility was able to reduce a potentially 3-day outage down to 3 minutes, right? So something like that has the ability to save lives, right? So I'm not disputing the fact that we need this technology. But you can see the backbone, right? So this is that communications infrastructure that supports the grid. So we call this the electronic security perimeter. So this could be your substation or power plant. It could be controlled locally or remotely. Wink, wink, nudge, nudge, right? Things aren't always air gapped. And then we have our control center LAN, we have a DMZ, and then a corporate LAN, right? To get this information over to where your business entities, software assets can actually use the information that's out of the grid. So in a lot of cases, these systems have to be connected. There's ways to connect it securely and get this information in one way, but it has to be connected to fully realize the business case of these technologies. So as far as a cyber asset, any programmable electronic device, including, so you have your devices, you also have the hardware that goes in those devices, right? So this is your I/O cards, network cards, CPU, RAM, any kind of software, and the data. So this is actually the regulatory definition of what a cyber asset is in or for the electric utility industry. And there's something really curious about a lot of these cyber devices that control the grid, right? So let's look over here on the left. We have laptop computers, switch, media converters, firewalls. So most pretty much everybody in this room, right, works with these on a daily, if not every minute, right, of your day. And sometimes work at night, right, in your head, dreaming about these things. So radio, right? We have radio. Some people say, oh, well, that's air gapped. RTU. So this is really what we're calling that middleman of the grid. We also have a relay, a meter, and then PLC, or programmable logic controller. And I teach a class, an 8-hour course on T&D, transmission, distribution, cybersecurity, and I use this slide. And the reason is because what do all of those devices have in common, right? I use this slide because I want people to understand, what do all of these devices have in common? Things have to communicate, right? There has to be some interoperability. So what that means is the hardware, in a lot of cases, have to be the same, right? I want to now have an IP-based network inside my substation. Oh, wait, but IP is also used on my laptop. Well, now I have to have some very similar software that's also on my laptop on my substation relay, okay? So that, basically for that interoperability, so you have hardware, you have drivers, right? You have network, memory block, there's some kind of file management. That's pretty scary. So we have system call interface. So basically there's that hardware level, there's a kernel level, and then there's a user level, right? So this is pretty common across all these technologies. And the next question, do the vendors write their own source code? Does Windows write all of their own source code? Right, I see a lot of head shaking. Macs, Linux, right? Do they all write their own source code? It's not feasible, right? So the question, what third-party software libraries and applications are being used, right? So when an engineer, technician, or operator, when they're interacting with that device, either locally or remotely, they're interfacing and messing with other stuff besides just the vendor's applications. So this is an example. When he logs in, he's doing it via some kind of pretty portal, right, that was from the vendor's secret sauce, which is based on some PyPAM, you know, for the authentication of your Linux, right? Because let's say that there's a Unix or Linux-based underlying embedded operating system in these devices. The HMI, the human-machine interface, I have some examples of that. That's built on top of Apache, right? Which is just built on the top of the HTTP protocol. And then the firewall is, you know, these are just examples, the IP route too. So I use this example too. Fun fact, Linux kernel, 19.5 million lines of code. And the other point that I make when I present this slide at other events, the reason I say this is because I actually had a conversation with an individual at a utility, and the conclusion was that if the device requires firmware to update it, it's not hackable, right? It was such, in this gentleman's mind, it was such an embedded device that if it required firmware, you couldn't hack it. It's like, okay. But this is what shows, right? This is what I'm trying to drive home, is a lot of these technologies that are inside of these IEDs, these relays, some of those are the same technologies that are inside of our laptops, okay? So, priority. What's the priority when it comes to industrial control systems like the grid, like the power grid? Whenever you have your back office IT, the priority is what? We call this the CIA triad, right, for InfoSec. Confidentiality, integrity, and availability, right? So I have to protect credit card information. I have to protect social security numbers. Does anybody, you think an engineer cares if the identity of an electron is going to get stolen, right? I mean, so in OT, operational technology, the priority is first and foremost availability. When you're in the back office IT environment, and this actually happened at a utility a few weeks ago, or a few months ago now, when the cyber attack impacted their back office IT, start unplugging, right? You can't do that in an OT environment, right? You can't just start unplugging safety systems, right? That's you know, no way to go. So you see availability, integrity, and then last, confidentiality. So as far as some of the examples, this is just building that context, right? I'm trying to build that, you know, what we're going after. So annunciator panel. Over here on the left, we have a physical alarm annunciator panel. we have basically n times 3 lamps. And the reason is because each lamp has color indications, right? So if it's orange, you know, caution. If it's green, everything's okay. Flashing red, oh, you know, you got to do something, right? So over here on the left, this is a physical. The problem is, oh, that's n times 3 lamps, n times 3 circuits that you have to build that close the contact to basically illuminate the diode or lamp. And then the issue, right? There's too many wires. There's a lot of wires. Is the alarm active, or is the alarm not active, or did the bulb burn out? Right? I don't know. It could be either one. Over here on the right, this is what it's being replaced with, software. So this is basically, it's one of 2 options. It's either a typical, a dedicated application, so Windows, Unix, whatever, based GUI, graphical user interface application, or it's a web page that you navigate to that kind of embeds that annunciator panel inside of your web browser. And then you expand it and it looks the same, right? It looks the same. The issues here, my first problem or issue or concern is, has it been hacked, right? In a lot of cases, the only concern is, what does all this stuff mean? Because a lot of times with these annunciator panels, you can see the log of alarms there at the bottom. You know, it's just massive, it's feature rich, there's a lot of settings. In a lot of cases, this is all up to the integrator to figure out how much they want to put on these annunciator panels. So that's the annunciator. This is an example of a one-line or single-line human-machine interface, HMI. So this is basically what an operator would see at a control center, right? So over here on the left, we have those panels that are inside that substation or power plant. You could go up locally, control, you know, open switches, etc. And all of that functionality and capability is now getting packaged and controlled via software and presented via a human-machine interface like that over there on the right. And that basically allows that remote control capability. And control and monitor anything, right? Anything with regards to the grid, power plants, substations, distribution feeder circuits, etc. So this is basically the grid's middleman. So this is what we're going after. This is that remote terminal unit. Okay, so RTU. That functionality that I just talked about, right? That annunciator, that operator's single one-line or operational one-line diagram, that is now presented via a smart RTU somehow. It could be an application that you have to communicate to the device and the data gets sent to this application and ran, or in a lot of cases, it's, like I mentioned earlier, some website. So now what that means, right, this guy, he's running a web server. I navigate to URL A and I get this graphical user interface. I navigate to URL B and I get this graphical user interface. And it allows me to control these aspects of the grid, right? Breakers, switches, PLCs, cat banks, you name it. You name it. Right? So not only that control, but that monitoring. So all control capability goes through these types of devices. All monitoring as well goes through these types of devices. Okay, so hypothetical scenario, right? So whenever we conduct an experiment, we have to build some hypothetical scenario around it. So let's say we have our control center communicating via the wide area network to our remote site, the substation. So here, this is basically that control center. So some things that are typical of a control center. We have our historian, SCADA, so this stands for Supervisory Control and Data Acquisition. A switch, some firewall, and then here's the remote site. There's a firewall, there's a switch, here's a local HMI, human machine interface. Here's a relay, so this device is actually what senses changes in the grid and sends the command to, let's say, open a breaker, right? This is the RTU, and so check this out. You remember I mentioned the RTU is like that middleman, right? He's like that middleman. So whenever a command is sent from SCADA, he first goes down through the WAN, through the firewall, to the RTU, and let's say the command was to control a breaker that is being controlled by this relay. So it goes from SCADA, switch, RTU, back up to the relay, right? Back up through the switch and then to the relay. Also, let's say the dotted line here, that represents a serially connected relay. okay, a serially connected relay. So same thing, SCADA, switch, firewall, switch, RTU, serial connection, bam, to my PLC, programmable logic controller, or to any relay. So IED, that's an intelligent electronic device. So hypothetical scenario. This is something I came up with just real quick. So this represents potential scenarios where the malicious actor has gained access. Okay, so let's step through these. One, vulnerable or misconfigured firewall. So this is your substation over here on the right. The firewall, the WAN-facing firewall, has a vulnerability or it's misconfigured. Oh, who's going to misconfigure a firewall? Well, it's happened, right? The example from the utility in Tennessee. We've seen it. And you know, probably not the utility's fault, right? It could have been the integrator, so I'm not blaming the utility there. Two, where's two? Two, right here. A compromised switch or other IED. So this is a switch that was purchased, let's say, on eBay, and they bring it in to a substation. Or better yet, let's say they went down to Best Buy and purchased it at Best Buy. Okay? What happens if a malicious actor goes buy a switch, plugs it in, installs a malware rootkit, packages it back up, brings it back to Best Buy, and then Best Buy just puts it back on the shelf, right? That's been seen, right? We've seen that before. And then the utility technician, engineer, goes to Best Buy, buys this switch, which, by the way, engineers don't buy switches at Best Buy. But you know, if they did, right, that now switch that has malware on it is brought inside of a substation. Okay? Which is reporting up to a C2, command and control, controlled by your favorite black hat hacker. Right? So now he's able to have his way in. By the way, you think that this firewall, typically, is it monitoring the egress or just ingress traffic? A lot of times, right, it's just ingress. It's just what's coming in. Okay, so that's two, where's three? Three, malicious laptop. So this is the engineer, technician, etc. They bring their laptop into the substation, and the question is it clean, right? What's running on it? Is it malicious? So in the industry, we call this TCA, a transient cyber asset. Okay, transient because it moves, bam. So the question is it malicious? We've seen vendors in these industries, control system industry, where the vendor themselves were hacked, but the engineers, technicians, we need those vendor software applications to communicate to the relay, right? So this is a standard watering hole scenario, watering hole attack, where the vendor software is compromised without the vendor's knowledge, and then when the engineer, technician downloads that, they could then introduce malware into these control system lands, right? That's been seen before. That's been seen before. So this is scenario 3. 4, physical access. You basically breach the PSP or physical security perimeter. Has been seen before, right? Where you just break in and then bam, you plug into a switch. I had a colleague that went out with some engineers a few years ago to a distribution feeder circuit right at the distribution center, popped open a box, no alarm, nothing. He plugs into the switch and he was able to pull up a screen of the control center. Right, so he was out in the field, and he didn't have approval to do this, but bam, he was able to basically remote back in. So that's 4, 5. This is what actually happened in Ukraine, stolen VPN credentials. So Ukraine, this happened twice a few years ago, if y'all don't know. The first ever publicly announced malicious threat or malicious attack that resulted in the loss of power. Okay, so the first one, 250,000 people lost power for 5 hours. First ever cyber attack to knock out the grid. This was in Ukraine a few years ago. So stolen VPN credentials, you basically pose as the authorized engineer, bam. Okay, so I said all that to say this. Okay, it doesn't matter, right? This, basically, where there's a will, there's a way. Let's not get caught up in the details of how they got in. The question is, let's figure out how to detect it and mitigate it, right? So in this example, we're basically going after, we're the malicious actor in any one of these 5 categories, right? So we're in and we do a scan and we find that there's a website. inside the control house or inside the substation, inside the power plant. Like, okay, what is this thing doing? What is it? So recon, right? We first just, ping sweep very slow to avoid any detection that they may have, right? So 192.168.10, 111 is the IP of this particular device. So let's say I don't know what this device is doing. So bam, I get that login screen, right? Interesting. So then I curl it on port 80, and I see somebody, people in the audience starting to rub y'all's eyes. So sorry, the the font is a little small. But this is basically curl on port 80. You get the HTML that's there on that website. Nothing too interesting, right? Some JavaScript, typical stuff. You see the form. Okay, good. And by the way, I had to blur out the vendor there, copyright. But then, so that was a curl on port 80. Then we do a curl on 443, right? So HTTPS, and this was cool because when we did this curl on this particular substation device, your browser sent a request that the server could not understand. Reason, you're speaking plain HTTP to an SSL-enabled server port. Instead, use the HTTPS scheme to access this URL, please. It's polite, right? These developers are so polite. But look at this, right? So bam, in this treasure chest of just doing this scan on 443, look at all the information that was revealed, right? Apache 2.2.9, OpenSSL, FastSGI, ModSSL, and Python. Okay, cool. Next thing I do is to see if this device is vulnerable to any directory traversal. So in the URL, just type in random garbage, 404 not found, the path was not found. Oh, but look, powered by Cherry Pie 3.1.2. So now I know, well, at the time I was like, okay, I need to use trusty Google to figure out, okay, what all is Cherry Pie about? So Cherry Pie is a Pythonic object-oriented web framework. So it turns out that this particular device was using Apache, but they were using a Python web framework to present those two GUIs that I showed you earlier, right? And those are similar, right? Those aren't the exact same ones, of course. But that enunciator and that one line, okay? So recap. Number one, unauthorized access. Number two, we only sent 2 requests, right? We only sent 2 requests. So the first one was to curl the IP at 443. The second one was to try to do some directory traversal magic, get IP/anything, and then we got all that information. Okay, that's pretty bad, right? That's pretty bad. So first thing we do, Cherry Pie, any vulnerabilities? So we actually looked at the GitHub code. By the way, that's open source framework. You can look at all the code. And then bam, we found this bug. A request get post when invalid protocol name HXXP instead of HTTP. So when you feed it a HTTP request, a legitimate HTTP request, but change that header to something other than HTTP, something happens, right? Something happens. So that's what we did. We went to our brewing magic pot, wrote some code real quick, and you can see this is our header. Instead of HTTP, we just said HXTP. Sent it the request, and here we go. So not much more information. We already know the Apache. I apologize for the people way back there. We already know this stuff, FastCGI, OpenSSL, the version of Python, the version of WSGI. So, okay, we already know all that. That's good to go. We get down here, but this tells us the exact function or module within Cherry Pie where it threw the error exception handler, and bam, right? So this gives us now more information that it revealed as far as the exact configuration, even the file structure of the device, right? If anybody knows what you can do with that, let's talk afterwards, because honestly, I'm not sure how much value there is in that. So we honestly, at that point, we treated that as a dead end. Basically, our nice shiny gem turned into a rock. So then we went down the list, started doing some CVE searches. So not much by itself as far as Apache 2.2.29. It really depended on what other modules and stuff were kind of packaged with that Apache version and how they were being used. And this is all we knew at the time, right? This is all we knew. So we're posing as the hacker trying to get after this device. And then we found this one, Apache 2.2.29 paired with mod SSL. So in Apache, I may cause a dereference, a null pointer when third-party modules call, blah, 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 blah. Okay. So it's like, oh, there's an error, there's an issue. Bam, back to the trusty potion. Let's try to come up with something. And what we did, so if you read the description, it basically causes this error during an HTTP request to an HTTPS port. Okay, so we did this HTTP request on port 443, just a quick connection, and nothing happened, right? We were all excited and we got depressed. We were really expecting something to happen, but nothing happened. So that was the response. It is a different output as far as what the device responded with, but nothing happened, okay? So new approach, right? New approach. If you're already in, can you do some man-in-the-middle type stuff, right? So because it was using HTTPS, it was potentially, so this is going back to the hypothetical scenario, that these certificates on this device were self-signed. Because a lot of instances, they're like, oh, these control systems are air-gapped, we can keep it self-signed, we don't need to change all that, da-da-da-da-da, right? So because it's self-signed, that traffic is encrypted, but there's ways you can extract that. So the scenario here, ARP poisoning, capture some network traffic, extract the self-signed certificate, decrypt the traffic, and are there any juicy bits? Turns out there are. Here's an example. So when you have the legitimate operator basically communicating to the RTU that's using HTTPS, the question is, what information can you gain by looking at that traffic? Right? That's the scenario, that's the question. And whenever you do this, you go in, decrypt the traffic because it's a self-signed certificate. We found that the URL request was to this specific URL. So for the gentleman in the back, there's the IP /scadasim.xml !_= Does anybody recognize that number? Before I go to the next slide. Okay. Who said it? Phone number? What's the other one? Okay, so we'll do it in a second. So what's going on here? So as you're monitoring this network traffic, doing this man in the middle, what we noticed was the client browser, so this is your operator technician, he first makes the request to the smart RTU, the remote terminal unit. So he authenticates, it's an active session, good to go. Then this web page that has the one line data on it, it responds with the graphics, the labels, the HTML, basically how it's laid out, right? How that GUI is laid out. But where's the actual values coming from? Where's the data coming from? Well, it turns out whenever this browser, this client browser requests the data, bam, gets the graphics back, bam, he then requests the data on another URL, right? That the actual data is requested via an XML page, and that houses all of that process data, right? So your voltages, your VARs, all of that data, breaker status, your alarms, switch status, that's where all that's housed. So we're like, okay, well, let's try going to it. And it turns out you're able, as the malicious actor, to see this web page, but you're not able to see this web page. Okay, so you can access the tag names, the analog values, the binaries. You can access all of that without being authenticated. And this is epoch time, right? So you can say /equals, change it, and you have all the trending value there for any instance in time. So that's basically that timestamp value right there. Result, unauthorized access to ICS, industrial control system process data. Okay, and now for something completely different. Back to basics, right? What was the title of this presentation? Just to knock it out, right? Just to take it out. Yeah, just take it out, right? I think all this was just making it a little too complicated. So DOS attacks, right? So simple Python script. Basically, if you have a legitimate session like your operator screen, He's in, he sees the substation, he's able to control it. You run this DOS, this Python script, basically it opens up a bunch of connections. What was interesting, it didn't DOS the operator, but it DOSed anybody trying to log in as a new user, trying to create a new session. Okay, so that was a cool observation. So that's why I only showed up for new sessions or requests. DOS number 2. So we have this web page. This is the auth login web page that I showed previously. And how many of y'all know formatted string vulnerabilities, right? So this is the printf stuff and C. And we just did, it's almost fuzzing, but not really. We just did a bunch of random strings on these inputs. And when we did it, it actually crashed that operator, right? So where not only did the operator lose the ability to see the one line, the enunciator, also any new users couldn't access the device until it was power cycled, right? So even if this, right, even if we stopped submitting these requests, it was a DOS, right? To where you literally had to go in and power cycle this device. Okay, so summaries, as far as mitigations, ICS tailored, so number 1, control systems, substations, power plants, we don't add more servers, right? We don't add more stuff on a regular basis. A lot of times these are static. These are really, really static networks, so there's no reason we can't have some kind of intrusion detection system that's able to detect any one of those 5 scenarios that I explained earlier, right? Any one of those 5 scenarios. As well as number 2, engineering, right? You can actually go in and secure these grid edge devices. You can adjust the settings. There's some cool technologies. Maybe we can do this on a future talk with regards to software-defined networking. If an attack is detected, you can start auto-segmenting your networks, right? That's a really, really cool application. And patch when and where possible. Patching is a huge problem in any industrial control system environment, right? It is a challenge. It's not, I mean, it's a problem and it's a challenge. Right, it is a challenge. So future work, there's a lot of rabbit holes right here. There's a lot of opportunities to go in and take a look at all this stuff, but so little time, so much to do. Some examples, reverse engineering the vendor source code. We actually have all of this particular vendor source code, about 90 or so %, right? We take the, dove in, took a closer look. Determine the exact exception handling error that's resulting in that DOS, and are there any other vulnerabilities that we can discover as far as going in and looking at the code? What else can be determined from the extracted PCAP file, right? So we noticed once you got in there and started decrypting stuff, you could see the session IDs going back and forth. So the next thing is, can we spoof that session ID and pose as the authenticated user, right? Examine all APIs and modules. So going back to that previous example, looking for more vulnerabilities. And can you send commands as a unauthorized or unauthenticated user? So that's not authenticated. Can you send control commands to the grid as an unauthenticated user? That's the next step, right? So this is an example of basically those inherited vulnerabilities. So for this particular device, once we got in, we started looking at all 120 third-party libraries that it was using, and 45 of them, a little over 45, had known vulnerabilities, right? So these were known vulnerabilities in these software libraries that they were using to make their own secret sauce, okay? We are right 15 minutes till. So any questions, comments? Yes, sir?
What was the second one? You said reverse engineering, and then these are...
As far as the future?
Yeah, PCAP, or is it analyzing PCAP data?
Yeah. So analyzing PCAP, you know how we took it, Wireshark. So can you spoof the session ID, right? Because all that traffic's going back and forth with the authenticated user. So can you take it and play it back? Yep. Yes, sir.
So were you actually able to get in between the operator and the RTU?
Yeah. So, well, that's the scenario, is that you're already in the middle.
Yeah.
There, and that goes back to those 5.
You can just do the,
I mean, you could.
movie attack where you override the HMI and show them whatever you want to show them, so that if
Yep.
you're causing havoc on the grid and the operators only see that everything's green.
Yep. So you can use something like art poisoning, right? To just, so yeah, there's all these different scenarios, but going after the specific device is what we were focused on here, versus just feeding fake data back, you know. Yep.
Well, it's just what's one step in a different, you know, into the attack campaign itself.
Yep. Yep. So I mean, the moral of the story, right? These are systems. They're good. We need computers in the grid. I'm not advocating against that, but it has to be engineered for security. It has to be engineered with security. We have to understand these risks, right? So we can make these business decisions. And I mean, it's a new world, right? Brave new world. Yep. Good question. Maybe we can discuss that offline. But no, there are a few, I'll say this, domestic-based vendors here in the U.S. That seem to be have a little bit more, up the ladder as far as maturity with securing these devices. And I think the challenge really goes back to what's the priority? The priority is availability, right? So when we take some of these technologies that are used in the back office IT for security and start shoving them in these devices that control the grid, a lot of times we do lose some availability. An example of that, there was some technology, a new smart grid protocol that was installed. Some people tried doing a pen test on it, and they took 500 substations offline. Right, 500 substations offline. And it wasn't necessarily obviously that could be used as a security, issue, or that could be classified as a security issue, cybersecurity issue. But it was just a protocol, right? Just protocol. All right. Any other questions, comments?
You see that most of them are still using third-party libraries, or any people doing total vertical?
There's one particular vendor that's looking at total vertical, but I hate to see what their investment costs are. And they're actually having a challenge as far as cost of entry into the market because they don't have that interoperability, right? They don't have that interoperability with other protocols, other browsers. Yeah, because right? What did I say as far as how many million lines of code? Yeah. Yep. So, not yet. Heard about it, but yeah, I haven't seen any as far as control systems either in a power plant or substation. Right. I'm not saying they're not in other ICS environments, but you're I'm just focused on the power grid. Any other comments? Questions? All right, thank you.